Eric Burgess here. The average for a study is 14,000. Assuming a normal distribution with a standard deviation of 3,500, find A, the z-score for 15,000, B, the z-score for 10,000, and C, the data value for z equals 1, z equals 1.7, and z equals negative 0.5. So we're looking at this and immediately we see we're dealing with z-scores. So our first train of thought should immediately go to the z-score formula. So the formula, I always encourage writing down the formulas you're going to use because it gets you familiar with how they look and which ones you need and when. Because right now you're in the section that uses it, but later on they're going to have like 10 different formulas you could pick from. So it's a good idea to get familiar with them. So doing this sort of helps you remember them. So z is equal to, and then we have our data value minus the average divided by the standard deviation. Now I am using the sample version of the formula, which it doesn't make a difference for this particular formula if you use population or sample. But the reason I'm using the sample version is just because it's a study, and with studies, you generally don't study the entire population, or if they do, usually that's stated because that's kind of a bit more out of the ordinary. And so I'm being conservative and going with the sample version. For this stat, it doesn't really matter, but for things like for standard deviation, right, that makes a difference. For other formulas, it can. So, and it's good to think about, what level you're working on every time. That way, when it does matter, you don't accidentally make that mistake. So just give a little thought to the sample versus population debate every time. So that's what we're going with here. It's a little ambiguous, doesn't really matter for this problem, so we're good to go. We're going to go for A. So A says, hey, get the z-score. Well, we've already got a formula that has z equals, so we're good there. And we want it for 15,000. So we say, okay, well, z for 15,000. Well, let's find it. So we need to ask ourselves, what are these numbers here? So these numbers here are data values, and they want to find where they lie relative to everything else. So, right, the data value would be here. We're going to take off the average, and then we're going to split it into pieces. That's what this division by S is. Division of standard deviation splits it into these standard deviations. So it's like we have a line, and then we're splitting it into pieces of size S. And S, so if it's like 3S away, that like means something. We're like, oh, that's pretty far away. But if it's only 1S away, like here's our average, the mean, then we say, oh, that's actually pretty close to the mean. It's not as far away. And so it's pretty useful to talk about units of standard deviation, how many S's it is. That's why we divide by S right there, the standard deviation. So let's write down what our values are. So we've got the average. So we have X bar is equal to 14,000. We've also got S, the standard deviation. We're told that's 3,500. And we're told our X values are right here. So right, they're going to give us X values to plug in to pump out Z scores. That's the goal here. So we say, okay, well, the first one's for 15,000. So we say, all right, well, let's do that. Z is equal to 15,000 minus 14,000. And then we're going to divide by 3,500. 3,500. That's our S, right? So we just plugged it into the formula. And when we do that, we're going to get a number out. We're going to get a z-score out specifically. So we're going to do the top 15,000. We're going to subtract off the mean, 14,000. So we're above the mean, right? 15,000 is greater than 14,000. So we expect a positive number. And then we're going to divide out by the standard deviation, 3,500. All right, and I'm going to go to 2 decimal places because most charts only go to 2 anyways. So we're going to go to 0.29. Some charts go to way more, and it's always good to have a little more accuracy. Do whatever your instructor encourages you to use. So next up, we've got B. This is going to be Z is equal, and it's the same deal except they changed X. X is now 10,000. That's the data value. They say, hey, where does this data value lie within, how close is that in terms of z-scores? So they say, okay, well, 10,000. Remember, z-score is kind of a useful way of talking about how far away is from the mean. but it's kind of standardized. It allows us to get rid of the fact that the standard deviation could be different sizes. It sort of takes that out so we can directly compare stuff. So we've got 3,500. We got our standard deviation and our mean. Let's go ahead and do this. So we're going to do 10,000, 1, 2, 3, minus 14,000, 1, 2, 3, and we get a negative number, right? That makes sense because this is smaller than the mean. So we're going to be below the mean, which for z-scores is below 0. We expect it to be below the average. And we're going to go do that. We're going to get negative 1.14. Now, last time I said 2 decimal places, so I'm going to do the same thing here. And so this would be the z-score that would go with that. So, okay, doing that, let's go on to C. So C is a bit different. They want the data value. Let me move this down. The data value for z equals 1, z equals 1.7, and z equals negative 0.5. So this one, we're given a z-score, and they want us to produce an x. So recall that the formula for the data values is we need a formula that has x equals 2. So to do that, there's another formula, right? That's going to be the mean plus the z-score times the standard deviation. That's a S, by the way. It's not a 5. It's an S. Whatever. It's an S. And then that is going to be equal to x. This is the formula you need. You could solve for it, right? We'd multiply by s and then add the mean. And that would give us x if you want to solve for it. So, okay, knowing this formula, we can plug in now different z-scores and get out x values. So our mean is 14,000. We're going to add to it the z-score. So the first one is 1 times the standard deviation, 3,500. This will give us out the x value. So if we have a z-score, we can go back and find the data that corresponds with it. It's really, really important that we understand that we can go backwards. All right, so let's do this. We got 14,000 plus 3,500, and we're going to get 17,500. Did I put too many zeros down? Nope. It just seems like a big number. But that makes sense, right? 3,000. Yep, that's good. That's good. All right, so this is for the first z-score. Then we have the same formula, right? The only thing that changes is the z-score. 14,000 times 1.7. That's our next one. Times 3,500. This is going to be equal to something. So let's go ahead and do that. So we've got 14,000 plus, and this time we've got a number that's not 1, so we have to write it in. 1.7 times 3,500. And you see, you can just write it exactly as it appears. Use parentheses when you sub in. It'll help you avoid mistakes. And we get 19,950. So this would be the data value that would correspond to it if we were 1.7 standard deviations above the mean. And we can do that just having the z-score. So you can think of the z-score as just the number of standard deviations. 14,000 plus, and then our last one here is negative 0.5 times 3,500. So again, just plug in the formula, easy peasy. I'm actually going to just copy this, and I'm going to replace this with negative 0.5. So this calculator has a separate button for the negative, so make sure you use that. Negative 0.5. And we do that, and we get 12,250. And this would be the answer for below. So there you go. That's how you do a question like this. So if we want to find the z-scores, we're going to need to plug in x values. But if they give us z-scores, then we need a formula that will give us the x values back. So you can go both ways. You see, we can get a z-score, or we can get an x value. So this is very, very handy information. If you have any questions about this, feel free to drop a comment down below, subscribe, and hit that bell icon for future videos, and we'll catch you in the next problem.